Okay, so back to reinforcement learning. So today, it's the same day. We're going to start talking about MDPs or Markov decision processes. So recall in the last lecture we talked about reinforcement learning for the first time. At a high level, the reinforcement learning has an agent that has to make decisions. These decisions are governed by a policy, and this is with respect to an environment that the agent exists in, at which each step the agent provides a action to the environment given a respective state that it's currently in. The environment will then respond to the agent with a reward signal as well as a new state. As we talked about in the last lecture, some reinforcement learning algorithms do not involve a state at all, but Markov decision processes do. And this lecture we're going to start talking about kind of the framing of this problem. And over the next few lectures, we're going to talk about how do we solve some of these how do we evaluate how good a policy is? How do we evaluate the value of being in a particular state? How do we evaluate the value of taking a particular action given a particular state? And so on. As you'll see in the bandit case, we saw kind of a simple version of a lot of the questions that we're going to be asking, and that's why one of the reasons that I like talking about bandits first. There's actually a book that I highly recommend called Reinforcement Learning by Sutton Barno, or yeah, Bardo and Sutton. It's kind of I guess, seminal book on the subject. Highly recommend it to check it out. But it also kind of follows that same path of let's talk about bandits first, and then let's talk about Markov decision processes. So again, let's revisit this high-level picture. And again, as you'll see, I've linked Lillian Wang's blog posts here. I really highly recommend you all check it out. They're very, very good and a good overview of a lot of the material that I'll be going through in this course, in this part of the course. So to recall, right, we have an agent initialized in a particular state of 0 or S naught. The agent selects a particular action in the action space, and then the environment responds to the agent with a reward R as well as a new state. So again, what we want to do is we want to maximize the expected rewards respective to the possible distribution of states and actions that our agent can essentially see over a particular trajectory. A trajectory may be, a finite horizon trajectory, meaning it ends after t steps, or we may go on forever. So in other words, we want some kind of algorithm that's going to be exploring an environment for effectively forever, and we want that algorithm to improve over time without having to stop. So there's a bit of a kind of thing. We'll talk more about this in the future lectures about how to deal with episodic and non-episodic situations. So again, like as I mentioned in the last lecture, reinforcement learning has a lot of like these nuances where the high-level idea kind of stays the same, but is it episodic? Is it not episodic? Do you know the model? Do you know the policy? Like all these different things that if you know this and you don't know that, there's kind of this big rubric of choices that you have in terms of what you can do. So to talk a bit more formally about a Markov decision process, and if you might have come across these already. For example, a finite state machine is a Markov decision process, but the finite state machines has sort of these discrete things where you're in a state and you can go within a logical constraint to a particular set of states from that state. Whereas a Markov decision process is a more general kind of definition of this, where you can be in a particular state and have a transition model or a probability of going from one state to another state given an action or given a logical constraint. So it's a bit more fuzzy than a finite state machine, but we'll talk about it kind of more formally here. So a Markov decision process M, which is defined by a set of states S, a set of actions A, this probability transition function, a reward function, which is a function, by the way, of state and action, and then also this discount factor for future rewards. This discount factor generally is between 0 and 1, and usually it's less than 1. If it's 0, then that means that we are super opportunistic, right? And in other words, this discount factor is what you multiply delayed rewards by. So today I get a reward of 5, tomorrow I get a reward of 10, and whatever. So in the case of the gamma, the discount factor being 0, I will multiply my all future rewards by 0, which means that I only care about what I get this very action time step. And you can kind of imagine this being problematic because in many cases I have to take many different actions that perhaps return nothing, and then I get a reward. So that sort of delayed gratification is sort of encapsulated by this concept of gamma. In some cases, you even want to do gamma is equal to 1. But the problem with that is that if I can wait forever to get the reward, so in other words, imagine I do something for 1,000 years and then only on year 1001 I finally get to the gold nugget, and I win, right? That's taken me 1,000 years to get there, but from the perspective of the algorithm that we developed to do that, it's going to be just as effective as if I got the gold nugget on day 1 because of that sort of gamma being 1. Whereas if gamma is less than 1, right, as it accumulates over time, it eventually gets to 0. So the value of being able to discount your future rewards and kind of pushes you or kind of encourages the agent to explore faster, right? Whereas if you have a gamma of 1, you're not penalized for sort of ambling about and sort of Brownian motioning yourself to a situation where you then receive a reward. So you can imagine a gamma of 1 is a jellyfish, a gamma of 0 is of like I don't know, a tiger or something that has to kill now or it dies, something with very opportunistic mindset. So yeah, that's sort of a high level on Markov decision processes and kind of the things that we're going to be seeing throughout the next few lectures. So as we talked about, a policy is a function of the state that we're currently in, and it's sort of a probability distribution across what action should we take given a particular state. So a good policy will essentially allow us to maximize the rewards that we see over a period of time, as we'll talk about in the next few slides. And can be a probability. So it's not necessarily, you can have a deterministic policy, meaning, so say I'm in a particular state, I take this action, that's possible. Or you can have a probability distribution such that in a particular state, 10% chance of taking action 1, 10% chance of taking action 2, 80% chance of taking action 3. So we're kind of heavily skewing action 3, but maybe we'll take action 1 or 2, and then we sample that distribution, and then that chooses which actual action we take. And so, this is choosing an optimal policy can be very difficult, right? Because ultimately, the actions that we take determine what the distribution of states we see is, and the distribution of states we see also determines what reward function we ultimately see. So within a given state, we may see a variety of different possible rewards because the reward is given to us based on us entering a particular state. So how do we evaluate whether or not a policy is good or not, right? Given all of those sort of variables in our mind. So one way is what's called the state value function. And so we can evaluate what's the value, or we can define what the value of being in a particular state is. So formally, the value function under a particular policy pi of being in a state S is going to be equivalent to the expected value of the return g of t, where S of t, or the state that we've taken, is S. So g of t, or the return, is defined as the sum of discounted rewards over the horizon of our trajectories. So in the case that's shown here, we have g of t is equal to r of t plus gamma times r of t plus 1 dot 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 times, and we kind of take gamma to the power. It's like you're multiplying gamma by the next one and the next one and the next one. And again, where this gamma is this sort of constant discount factor, which is between 0 and 1, as we've discussed. As you can kind of see, in this case, the return given a gamma of 0 would simply be just the immediate reward that we see in that particular S, in that particular state that we're in. We wouldn't care about the future rewards from that point. We'd only care about the state that we're in now. And if gamma is equal to 1, then we would basically just add the sum of all rewards that we could potentially see from that state forever. And so you can kind of see this is a good way to determine the value of a particular state that we're in. One thing I should comment on here, which I didn't discuss earlier, is you'll notice that we don't talk about rewards previous to the state that we're in. So in this case, you can see S of t is equal to S, and the return given respective to a particular state is the sum of all the rewards that we'll see in the future from that potential state. We don't talk about rewards that we've seen up until that point. And so that's something to kind of talk about with regards to the Markov decision process. The Markov assumption, the assumption that the Markov decision process makes, is that our future rewards are not going to be affected by past states or past action. So in other words, at every time step, all I'm looking at is the future. I'm not considering what's happened in the past. This is not always true, right? Most things, we care about the past. Most human beings make decisions today based on what's happened before. So this assumption is a very, very frail assumption. But the assumption that we're making here allows us to determine whether or not a particular policy or a set of decisions will serve us in the future. So it's a bit of a, even though it's not intuitively what human beings do to determine what they should do next, it is a good way actually to make decisions, right? So in a way, you want to consider your experiences in the past to determine your policy that you're going to use today, but you don't actually want to consider those past experiences in terms of the decision that you're making, in the sense that the way you make your decision is affected by those past experiences, but the decision of itself is independent of those previous state transactions and those things. So it's kind of like a Zen mindset, right? Like, we learned a lot of things in the past, but we're not going to let them affect our future decisions. But we are going to use that wisdom in making better decisions in the future. So kind of a cool metaphysical kind of concept here. But in the context of MDPs and reinforcement learning, we've defined that our return for a particular state is only in the future. We're not going to consider the returns and the value of having gotten to that state. We're only going to consider the value once we're in that state. And so this is the very, very powerful way to kind of think about evaluating a policy, because our value function is going to be directly determined by the policy that we observe, right? Because ultimately the policy that we utilize will determine the set of states that we see in our trajectory, and those set of states will directly result in the rewards that we then observe from that point on. Another way to think about evaluating a policy is what's called the state action Q value function, or the Q function, more kind of shorthand. It's very similar to the value function, except we make a slight adjustment here. So the value of the Q function sort of says, I want to know what the value of taking a particular action given a particular state. So in this case, this is a little bit, I might have kind of misrepresented this on the slide. One moment. Yeah, my apologies. This is correct, but it's a little bit confusing. So in this case, the value of this action that you're going to take is going to be equivalent to this next state S prime that you'll see respective to the action that you've taken. And this is encapsulated in this bottom equation here. But in terms of the return, you can kind of imagine the return in the context of the Q function is going to be equivalent to the return that we see given that we're in a particular state that we result in given this action that we've taken, and then all of the different values from that point on. So it's almost like the return here is going to be equivalent to the return of that particular state that we've entered due to this action plus the value function of that new state that we're in. This is actually kind of, we'll talk more about this in the next lecture in particular about the Bellman functions, but you can kind of see here that we can define the value function in terms of the Q function, which given the expected value, which is essentially the expected value of the return, which is defined as every possible action or the distribution of actions across all actions times the value of that particular action. So it's sort of like saying if we're in a particular state, then the value of being in that state is going to be equivalent to the expected value across taking every possible action and the value of being in those new states respective to that action. That's sort of a way to think about it. Again, you can see a lot of little nuances here, but these definitions do kind of really check your intuition about what's going on here. In other words, more simply stated, the value is going to be equivalent to the value of taking the different possible states, the different possible actions, and what the value of being in those new states might be. I know I've repeated myself like 3 times different ways about this, but trust me that there's lots of different ways to think about it, and I think it's valuable to kind of go through this repetition over and over again. So one kind of last function we'll talk about before we kind of take a look at an MDP and sort of explore it a little bit is the advantage function. The advantage function, kind of stated simply, is the value of taking a particular action over the value of being in a particular state. So it's sort of like saying, hey, we're in this state. If we take an action from this state, what's the value of taking a particular action given a state versus the state that we're in? And so what's the advantage? So if this is, positive, that means that perhaps that's a better action that's the best action to take. It's sort of a way to evaluate how good the action that we're taking is, respective to the states that we're going to see over our particular policy. You can kind of see, one thing to think about, right? The value function of a particular policy on a given state is just going to be a value. It's going to be g of t. But the value of q given a particular state is going to be a vector, and that vector is going to be a variety of different actions. The value of taking a particular action, right? So say we have 10 different actions, right? The value of taking a particular action given a respective state, we'll have 10 different values. And so in that sense, right, you can kind of imagine that this advantage function then is also going to be a vector. And then we can use that vector to figure out, well, what's the most advantageous action to take? And that's why it's called an advantage function, because we're going to take a look at it in the context of what's the best action we can take. We've seen a lot already, and in fact in the bandit lecture just before, that this function, this Q function, is very similar to what we saw in the bandit lecture, except that Q function only had the state, the action. There was no state, right? So in this case, this is very similar to how we would potentially choose an optimal choice, right? If we have this function and we know what the possible value of taking all these different actions may be over the state value, then we can say, well, this particular action is the best and the most advantageous action to take. And that's one way to perhaps choose the next best action. But for the time being, we haven't really discussed how we may learn a policy or how we may optimize these functions. We'll start talking about that in the next lecture when we get into Bellman equations and the Bellman backup. But for the time being, this is really just about providing some insight as to how to determine what actions may be better, how to evaluate states, how to evaluate policies, and how to think about the way that we would maybe perhaps make decisions or evaluate decisions inside of an MDP type of context. So here's an example MDP. An MDP is essentially, like I said, a state machine. It can have kind of complexity. This one's going to be, there are no transition probabilities, but keep in mind that the other bit of an MDP we talked about just for a second was this transition probability. So given a state that we're in, what's the likelihood of transitioning from that state to another state? And that probability can be deterministic. So we can say, okay, going from state 1 to state 2, the probability of that happening is 1. But they can also be stochastic, which sort of is a really important thing to note, right? Like imagine being on again, like a frozen lake, and I want to go to the left, but I start moving and I don't actually go to the left, or some kind of behavior. I employ an action to then result into a state transition, but the state transition doesn't behave the way that I would like it to. So that's one of the things to kind of think about, that an MDP is also defined by this transition model that we may or may not know, right? It may be deterministic, it may not be deterministic, and that's something important. As we talked about before, right? MDPs have this Markov property or the Markov assumption such that the probability of going from state ST to ST plus 1 is the same as going to the probability of going from ST plus 1 given a trajectory of a variety of different states terminating in ST. In other words, these previous states do not affect the transition probability of the future. And again, remember that the way that we get reward is by entering into a state, and so the rewards that we see are a direct function of the states or the state distribution. And so the Markov assumption, kind of stated more clearly, is that it is doesn't care about the past, right? It only cares about the future and your transitions, and therefore the rewards that you see only care about the future and not about the current, the past. So taking a look at this sort of fun sort of example of a Markov decision process, say you're asleep, right? And you can have this reward of hitting snooze of 1, right? Remember this discount factor. So if our discount factor is 0, then I'm never going to get out of bed, right? I'm only going to care about immediate rewards. And so I'm always going to say, oh, hit snooze, hit snooze, hit snooze, because waking up incurs a reward of -1, right? And then I move over into this state, whatever that is, and I can maybe call in sick, doesn't cost me anything. And then I can be in this sort of perpetual hedonistic cycle of calling in sick, reading Twitter, watching soap operas, going back to bed. So you can kind of also see this is not very realistic. If I do this enough, I'll get fired, right? But whatever. So then there's this sort of alternative state I can go into, which is going into work, which costs me something, and I kind of then now go into this painful, some reward and some negativity. But if I succeed and I kind of navigate this properly, over time I'll kind of hit this go to bed, because you can see this this path here: wake up, go to work, work a little, and then go home and go to bed. That's -1, -2, -1, or a total of -4. This is +5, and now I have 1. So in other words, this path is equivalent to hit snooze in terms of total rewards if my discount factor is 1. If it's less than 1, this is going to be slightly less than 5, but hopefully more than. This is going to be slightly less than 1, but hopefully more than 5. So this is going to be a more appealing route. But you can see that the expected reward of doing this, once in a while perhaps, I'll ask for a promotion and I'll get it, and then I can get this reward of 50. So you can kind of see how we can sort of evaluate all the different state transitions and sort of try to determine, even like, a human being can just look at this and say, okay, here's some strategies and this is what's going to maximize my thing. And over the next kind of few lectures, we're going to look at ways to actually deterministically or asymptotically determine a policy that will maximize your potential reward given this sort of MDP and these transitions. So yeah, you can kind of potentially evaluate, like see that there's a very kind of a lot of synergy between this and game AI, in the sense that game AI, these transitions are sort of deterministic, but given a sort of behavior tree like this and an RL algorithm, perhaps you can come up with a more realistic way to explore that in a way that sort of agent maybe can respond to unexpected states. So this is kind of a hard-coded thing, and if you had an AI agent that was scripted to do this, if you added a new state over here, it will never go there because it'll just not know what to do with it. But with an algorithm that kind of learns on the fly, it might be able to sort of evolve to deal with states like this. And more interestingly, as we'll talk about in a few lectures in deep learning and applying this reinforcement learning, applying deep learning to reinforcement learning, we can deal with continuous state spaces. We can deal with continuous actions, and kind of making predictions across much more complex scenarios. So yeah, next lecture, which I think will at this point I'll record tomorrow, will be on the subject of the Bellman equations. And the Bellman equations are a way to approach these problems in the context of dynamic programming, and was sort of the basis and the start of a lot of this reinforcement learning stuff. And it still is the way that a lot of this is done. So there's not too much has changed. And if you've done dynamic programming before, you'll probably see a lot of very similar ideas exhibited in the next lecture. So yeah, thanks for watching.